With that, we'll go ahead and move on to Dr. Frame. She is the Director of Cognitive Research at Parallax Advanced Research, working as part of the Joint All-Domain Integrated ISR Group at the Air Force Research Laboratory. She obtained her PhD in psychology from Miami University in 2017 and an MDA from Wright State University in 2020. Her research specializes in mathematical modeling of decision-making, leveraging a variety of physiological sensors and behavioral data to better understand higher order cognitive processes. So with that, I will turn it over to Dr. Frame.
Hello, thank you all for being here today. I think Dr. Lyons and Dr. Robinson did a great job introducing the topic of human-machine teaming, so I'm not going to belabor the definition, but I was planning to speak to you all today about a little bit of what my research group does pertaining to human-machine teaming and our collaborations with AFRL, with NGA, DARPA, et cetera, and just give a broad overview of some of the studies that we've done in the past and how they impact human-machine teaming. So next slide, please. So first, I wanted to get into some of the more specific topic areas because as has been introduced by the previous two presenters, this is a humongous topic. There's a lot of things that encompass human-machine teaming studies. So some of the things that my team has focused on and are of deepest concern to us and our customers are looking at things like, what are the shared goals between teammates? You know, we know that humans and machines are each being asked to do different tasks, but what are the shared goals that they have, and how do each of those agents sort of mentally model what is their task, what is the goal, because you can sometimes have discrepancies between how a human understands their task versus how an autonomous system understands the task. There's also the concern about keeping all teammates in the loop so that if a failure occurs, someone can quickly and adaptively respond to that issue. So that can be a problem if you're each specializing on your own task with no awareness of what the other's doing. Then when a catastrophic event occurs and you're asked, okay, take over their tasks, you can't do that if you have no cognizance of what the other teammate was doing. There's also the issue of trust between teammates. So you don't want the issue of humans over-relying on automation that is not doing its job effectively, nor do you want them to have to babysit the automation, because at that point you really get no benefit of efficiency of even using the automation. We look at issues of transparency and how do we present how the AI sort of understands their processes and how it's accomplishing tasks. How do you communicate that to the human teammate to allow them to adequately trust their automated teammate, because that might be doing something in a different process that they use. We also want to be able to recognize changing conditions in the humans or the machines. So if a decrement is occurring in performance, if there's increased cognitive load, even if you have an issue of like underload where you've got something like the person is bored and no longer engaged with the task, we want to figure out how do we inject certain appropriate interventions or change the task or, you know, alert the human, whatever needs to be done. Also balancing workload appropriately, changing tasks dynamically. It could be appropriate at a particular time that even if the human was doing a certain task, maybe they were doing it great and now they're not, and it needs to be offloaded to another human teammate or to an automated teammate. Even if that automated teammate isn't as good at the task as the human is, maybe it's important for them to take over it for now because the human is absolutely tanking on it. And then also we have issues regarding, especially in the military, we want to leave a lot of our final decision-making authority to the human operator, even within these human-machine teams. So it becomes really, really important to make sure that the human is getting all of the best possible information that they can, even when there's automation doing some of these tasks. So if the automation makes inferences, that needs to be handed off to the human as well, because they usually have the final decision-making authority. And also we want to look at measures of effectiveness. So how do we determine that this human-machine team is doing well? What is our measure of success? So these are all sort of front of mind issues for my research team and our customers and the research that we do. So I'm just gonna, in the next few slides, talk about just broad overview, high, 30,000 foot view of some of the studies that we've done in the past. Next slide, please. And just to note, all of these have associated publications. So if you'd like to know more than what's presented on these single slides, all of these are published works. So the first thing I'd like to talk to you about is a project that we have that we call the Autonomous Manager. And so this was looking at essentially the research question of who should be in control of which tasks when there are multiple tasks that could be allocated to human and automated agents. And then how do we reassign these tasks when performance starts to suffer? How do we dynamically reallocate this between human and automated teammates? So in this particular task, there were 4 essentially image search tasks where you emulating the ISR environment where we might be looking for a certain target of interest. And there were 4 that occurred, simultaneously. So they had to respond to each one by pressing either accept or reject. Basically, there is something in this image that I was supposed to find, or it's not in this image, like something like a blue car or a particular target, whatever it may be. And we had 2 different conditions here. One was an easier condition because each of these would refresh. They had essentially a limited amount of time to respond. So they had 8 seconds to respond on average in the synchronous condition, and in the asynchronous condition, each one of these panels refreshed at a slightly different rate. So one might refresh at a 5-second rate, one might refresh at a 9-second rate. And this makes it a little more difficult because they're not all changing at the same time. You really have to know how to prioritize each one and keep on top of a certain panel a little bit more than another. And in this one, we had a simulated automated agent that would take over when human performance was suffering. We also probed them every minute with subjective workload in this case, but we're currently working on some follow-up studies to use physiological indicators of workload instead. So in this case, they would be asked, are you feeling overloaded? Are you not? And depending on how they responded and their performance, certain tasks would be reallocated to automation. And we found that our autonomous manager, which was the system that made the decision between whether the human or AI is taking the tasks, was able to maintain a high level of team performance by reallocating tasks from the human when their performance began to suffer below a particular threshold. And we were able to maintain this higher level of performance consistently. And this was even under sort of suboptimal conditions. In this particular task, we had the automated agent as fairly unreliable. Its performance would vary between 50% performance and 100% performance uniformly distributed. So kind of a not great automated teammate, but even with that, we were able to reallocate tasks appropriately between the human and automation to maintain an acceptable level of performance. All right, next slide, please. So this is sort of an extension from the original autonomous manager task with the 4 independent tasks. And in this one, we were looking at what do these issues look like in a more realistic task space? And also, how should we program the decision-making algorithm of something like an autonomous manager? How should it be making those decisions between tasks? So for this tasking space, rather than 4 independent tasks, we had 4 interdependent tasks. So in the bottom left, or sorry, the top right image, you can see 4 panels there. In the bottom left, there's a screen with an X. That's essentially a psychomotor vigilance task that would flash a target that would tell them, okay, your target is, let's say in this case, a black X. They would have a visual detection task in the top left and an auditory detection task in the bottom right. So they had to determine whether the target was present visually and whether the target was being audibly stated in one of the audio channels. And then in the top right-hand corner, there's an integrated decision-making task that had a decision rule that required those 2 pieces of information and an additional cue. And with those 3 pieces of information, there were particular decision rules for whether to allocate a sensor or not. So in this case, failure on a task like the decision-making task could occur because they failed to integrate the information correctly or because they incorrectly identified. So it could be that it was present in the visual target detection task and they said it was not, and therefore they came to the wrong conclusion. So for this one, we needed the autonomous manager's thinking process to be a bit more sophisticated because we didn't want it to simply assume bad performance on this final dependent task is only because of isolated bad performance, but it could be actually due to performance that was incorrect on a prior task, and to allocate tasks appropriately because of that. And so this task was tested. We did some baselining with folks right before COVID, of course, with using EEG. And of course, because of COVID, we couldn't do a whole lot of human studies, but we were able to do some simulation studies. So in the bottom left-hand corner of this slide, you can see some model outputs. Essentially what we did is we studied various cognitive agents. So we gave simulated, sort of human simulated AI agents that utilized sort of different cognitive processes, had different sort of failure rates using different models. And we also had different autonomous managers that had different sort of thinking processes of whether to reallocate tasks based on just raw performance or based on simulated workload, et cetera. So we found that the greatest improvement in accuracy occurred expectedly when the autonomous manager had a highly accurate model of the cognitive agent, when there was a congruency between that rather than a mismatch, which makes sense. All across the board, all the autonomous managers performed better than chance. So having some kind of AI agent reallocate tasks was better than reallocating the tasks randomly. So that was just sort of a sanity check. We had a fairly rule-based system that we called the constant autonomous manager that was fairly robust across different cognitive agent types, so making different assumptions about how people would perform on the task. It was fairly robust. It was not usually the best model, but it was the most sort of resilient to different conditions, if you will. All autonomous managers struggled to improve performance for what we called our fatigue dynamic cognitive agents. So these were cognitive agents that performed a certain way, but we presumed that over time their performance would gradually decrement to sort of simulate fatigue. And that was difficult for a lot of autonomous managers to predict because people had varying decay rates, essentially. Yeah. So that sort of gives a little bit more of a flavor of how we start to probe these and try to get a little bit more precision for what's sort of the best solution. Next slide. Awesome. So in this one, we were looking at simulated recognition aids. And so this was sort of a research question of how well do some existing tools that we know are deployed in the field work, especially because sometimes they're not tested with humans in mind and they make certain assumptions. So we were interested in knowing, okay, where do some of these tools help humans and where do they start to break or fail? And so for this one, we had essentially a recognition aid versus a control condition. And the recognition aids we tested, one of them simulated Maven, which is a tool that essentially puts boxes around persons and vehicles within a scene. And we also had a simulated recognition aid that was essentially boxing all essential elements of information, which are basically just targets that an analyst is supposed to identify within a scene. And we were interested in knowing how this would affect EEI classification, as this is sort of the primary task that most analysts have to do. And we were interested in also seeing if it improved sense making. And sense making in this case was defined as essentially we had a scene that occurred. There were cues that occurred at the start of the scene that would give you hints of what was going to happen at the end, like a big event. And so what we did is we broke the scene in half. So we would have them watch a video for about 1.5 minutes. The cues would be present in the first half of the video. It would be paused. They would be asked, what do you think will happen at the end of this scene based on what's occurred so far? And so we looked at that as prediction accuracy. So if they accurately predicted the event, it was classified as correct. If they failed to identify, it was incorrect. And then we also asked recursively. So once they did get through the full video and they came to the end of the video and they saw what occurred, they were asked, can you identify what was shown to you in the video that could have helped you predict this event, essentially? So we were trying to look at sense making in sort of two ways, in the sort of prediction sense, as well as in the looking back and inferring what could have helped you determine this. And so we looked at whether accuracy was improved as a function of having these different recognition aids. And we found that EEI identification accuracy only significantly improved when EEIs were highlighted, rather than having all persons or vehicles. Doing that did not improve the ability to do EEI identification. We did find that sense-making accuracy, or at least in terms of prediction accuracy, improved with the Maven emulating recognition aid, but only when the key predictor of the event was a person or a vehicle and thus being highlighted. What we found from this is that automated recognition aids are most helpful when they're designed with a purpose, rather than sort of a broad-based approach of, box all of these things. It seems to be that if you want to improve performance on a certain dimension, you really need to tailor any kind of decision support system or recognition aid to that goal. Next slide, please. And then the last study I'm going to be talking about is what we called our path planning decision support system study. The research question here was essentially, how does an AI or machine giving a first pass of the data impact the human's ability to do quality assurance, basically? So in this particular task, we had a logistics task where because we were using novice subjects, we said it was sort of like trucking, delivering goods in certain to particular regions, and the trucks had to be allocated to regions on this map on the right. That each of those sort of highlighted locations in blue, yellow, and orange are associated with certain dollar amounts. So the goal is to maximize essentially the dollar amount return as a function of allocating to particular locations. And this was meant to emulate in military environments, essentially deploying ISR assets, because we have limited resources. They can't go everywhere. They can't collect everything. We want to get the best bang for our buck in terms of information gain. And in this particular case, using a proxy task with logistics, we essentially told our participants, hey, a bot has gone through this and tried to do the task for you, but you need to check it over and make any corrections that you think should happen in order to maximize the dollar amount and the points that you receive. And what we found is that human accuracy was highly dependent on the bot's accuracy. So sometimes the bot would be 100% accurate, other times 80%, 60%, or 40%. And we found that human performance was significantly higher when the bot was 100% accurate compared to any of the imperfect bots. Although it should be noted that even when the bot was 100% accurate, human performance was not 100%. So that's an interesting thing of it demonstrated that there still was a little bit of mistrust even in a perfectly accurate bot that led to inaccurate corrections. We also found that it had a huge impact on trust. So people did significantly trusted the bot that was 100% accurate significantly more than any of the inaccurate bots. We also tested different types of transparency into the automation's algorithm here, and we found that people had the most trust for explanations that were grounded in the actual task itself and were illustrated in the task itself rather than using a flow chart or equations. Next slide. So just to conclude, I have the information about my wonderful team. I'm very lucky to work with a lot of wonderful folks, both on my team and with our AFRL and NGA partners. If you have any questions, please feel free to contact me at any time, and I'm happy to answer any questions if you have them now. Thank you.
Thank you, Dr. Frame. We appreciate you presenting this morning for this opportunity today. Again, if anybody has any questions, feel free to post them in the chat, or you can raise your hand and come off of mute and ask Dr. Frame a question. Somebody is cameras on. I don't know if they're looking. Kathy Ashley, if you're looking to ask a question or you're not. I'm just looking through the attendee list.
No, sorry about that. No question.
Okay. I thought maybe you had a question. Okay. All right. Oh, I'm sorry, we do. So Frank Wolf asks, how do you model trust? Percent of 0.1 can be high risk.
Oh, that's a great question. So in this particular case, it was a fairly basic trust metric. We actually, since Joe Lyons is actually on this call, we actually used a modified version of Joe Lyons' trust instrument that looks at sort of trying to assess, like, would you use this, would you trust this in the future? Would you utilize this in the future? There's a variety of different questions that are trying to sort of probe at that sort of subjective response of trust, like, do you trust in this automated agent? So it was, for the purposes of this study that I presented here, a fairly basic self-report, but a fairly robust one as well that's been used in a lot of different studies looking at a lot of different potential automated tools.
Excellent. Thank you. Okay, any other questions? And again, feel free to email Dr. Frame there. Her contact information is at the bottom of this slide. And again, these slides will all be made available after the presentation. They'll be on our website. And you can also contact any of us through the OFRN website as well for that. So All right, I don't see any other questions. So thank you so much, Dr. Frame, for your presentation today.